Okay, guys. So we're going to start with proof number 2. All right. And if you guys would go ahead and write out the given, let's go ahead and talk about a game plan. All right. So what I am trying to do here, guys, is I'm trying to prove that this right here, all right, A, B, C, D is a parallelogram. Okay. Which means that I have to use one of the 5 different methods, all right, that we had talked about at the beginning of the lesson. So I either need to prove that the opposite sides are parallel, the opposite sides are congruent, the opposite angles are congruent, the diagonals bisect each other, or that one set of sides are both congruent and parallel. Okay? So let's talk about what we are given. All right, so we're going to delete that. Okay, so we are given that AB is congruent to CD. Okay, and I'm going to pause right there because that's pretty significant. So if you notice what I'm saying right here is that I have one set of opposite sides are congruent, right? So because I have one set of opposite sides are congruent, I'm going to go in either 2 different methods. I'm either going to prove that you have 2 sets of opposite sides that are congruent. Okay, so that could be one method that we're using. Or, all right, we could prove that one set is both congruent and parallel. All right, so those are our 2 different methods. Okay, so after that, we were then given, all right, that BC is congruent to AF. All right, and then we are given that angle AFD, and this is going to be a pretty quick proof, all right, is congruent to angle ADF. All right. So what I want you guys to look at, all right, is this triangle right here. What do you guys notice about it? What you should know, all right, is that you have a triangle with 2 base angles that are congruent. So what does that make that triangle? Well, the base angles theorem, guys, says that if the base angles of a triangle are congruent, then the triangle is isosceles. So what I'm going to state next is that triangle AFD is isosceles. All right. And that's by the base angles converse. It's been a while since we've seen that. And then if we know, all right, that triangle AFD is isosceles, then we know that you have to have 2 sets of sides that are congruent. So to determine that, remember we did the crisscross, all right, that said that those sides that are opposite of those angles are going to be the ones that are congruent. So that means that AF has to be congruent to AD. All right, by definition of isosceles. And then now let's take a look at our picture. So if you look at quadrilateral ABCD, all right, look at now what our notation is saying, all right? Isn't it true then that AD has to be congruent to BC? And that's through substitution. Okay, because look at your given, just so that you guys can see. All right, we have AF is congruent to BC. All right, and then we had AF is congruent to AD. So we just did a substitution there. Okay, all right. But now that we've proven that AD is congruent to BC, haven't we proven 2 sets of opposite sides are congruent? Which means then, all right, in this quick little proof, all right, that we have parallelogram ABCD. And that's because of opposite sides being congruent. All right, not bad. Okay? All right. Let's try proof number 3, and then we're going to be done. Okay, so if you look at your given information, once again, that does not look like a lot of information. All right, all we're given is that's a regular hexagon. All right, what? But it's actually a ton of information. Okay, so a regular hexagon, and that's our given information. Okay, so there's like a key word obviously in that given, all right, and that's regular. And we've talked about regular before, and what regular means is it's equilateral and equiangular, all right, which means that every single angle are congruent, all right, and every single side is congruent. So what that means, all right, is well, we're trying to prove, all right, essentially, guys, that this is a parallelogram, all right, which means we have to use one of those 5 methods, all right. But if I know that the hexagon is regular, don't I know that ON is congruent to KL? All right, so couldn't I state that in there? All right, that ON is congruent to KL, and that is through the definition of regular. And we're going to use that a lot, all right? So from here, guys, all right, we have one set of sides that are congruent. So that means that we are either going to use both set of opposite sides are congruent, or one set of sides are both congruent and parallel. All right, but what I want us to focus on are these 2 triangles right here. If I could prove those 2 triangles congruent, couldn't I then prove the corresponding parts are congruent, right? And so what do I know then about OJ, JK, ML, and MN? Well, because it's regular, I know that they all have to be congruent. So I'm now going to state, all right, that all 4 of those sides are congruent to each other. So OJ is congruent to JK, which is congruent to ML, which is congruent to MN. And I've had students that have combined step 2 and step 3 together, all right, and that's fine. I like the separation of them. I think it's a little bit clear, all right, but this is also by definition of regular. Okay, all right, so once again, we're trying to prove those 2 triangles to be congruent. So then what is the other component of regular that I mentioned? Well, the other component is that it's equiangular, all right, which means that all the angles are congruent, which means that angle J has to be congruent to angle M. And so, guys, that's also through, I told you we're using it a lot, all right, definition of regular. But once we've hit that, all right, can I prove these 2 triangles to be congruent? Yeah, I can do that with a little sass, all right, with a little side angle side. So I'm going to now have the triangle OJK is congruent to triangle LMN, and that's by sass, all right? And once I've stated that those 2 triangles are congruent, what do I know about the corresponding parts? Well, then I know, all right, that these 2 sides have to be congruent because of CPCTC. All right, so I can state now that OK is congruent to NL by CPCTC. And then now let's take a look at what we have in our picture. Don't I now have this parallel or this quadrilateral with 2 sets of opposite sides that are congruent? And the answer to that is yeah. All right, so then now I can state that this is a parallelogram, all right, OKLN. So that's a parallelogram, and that's once again because opposite sides are congruent. And that's it, all right? You can try all the other proofs. I think I have an answer key online, but I think those 2 are sufficient, all right, for this lesson.